Today, so now we will discuss the Poisson distribution, second type of discrete probability distribution, Poisson distribution. In the previous session, we talked about and we discussed binomial distribution. Binomial distribution we apply when there is a two outcomes, success or failure, two outcomes. In that instances, we use binomial distribution. Poisson distribution, it's like this. Here, in a shop, right? In a shop or textile, from 9 a.m. to 10 a.m. How many customers are visit to the shop? Or in the counter, bank counter, from 10 to 12 p.m. How many customers come to the counter, visit to the counter? Or how many customers use the ATM within a certain day or certain time, so within 1 hour or 5 hours or 24 hours or 7 days. In the bus, right, in the bus stand, how many passengers visit to the bus stand in a particular time period? Here, the time period is very important. In that instances, we use Poisson distribution, predicting the unpredictable. A manager's guide to the Poisson distribution, right? Poisson distribution. Mastering the mathematics of random business events. No prior stats experience is required for understanding these things. By definition, here, by definition, Poisson probability distribution. Poisson distribution is a discrete, right? Discrete probability distribution. This is used in situations where events occur at a random point in time space. Right here, very important. We can use in situations where event occurs, or event occurs mean how many customers are visits, how many accidents are happen in a particular junction in a particular period of time, like that. Event occur at a random point in time or space. For example, the arrival of customers at service station is an example of random occurrence in the time. Number of printing errors. So the type is normally type, type. So they do make mistake. So number of printing errors or typing errors in a page of a book. It's an example of random occurrences. Here, in the first example, is a time space. Time, it's a time. Here, from 9 a.m. to 10 a.m. or 9 a.m. to 10 p.m. So within this gap, how many customers visit to the shop? That is time. Here, the second example, number of printing errors. It is not a time. It's not a time. It's a book. Say the book has 500 pages. Out of this 500 pages, how many printing errors or typing mistake or printing errors may occur? It may happen. So that is not a time. The 500 page, that's a space, right? So the Poisson distribution can be applied for a given time space or given some time or space. So number of printing errors in each page of books is an example random occurrences in a space. So each of the above two situations represent Poisson process. Poisson process. So this one, this incident, this context called Poisson process. events happen randomly. For example, ATM. There are bank customers may visit to withdraw money or deposit money. ATM, cash deposit machine, or the bus stand. The passengers may visit. Your mobile phone, how many message, or WhatsApp, how many message you get a day. So randomly happened. You don't know who is going to message you, but on average, you get some amount of message in your WhatsApp. So those events are random events, but they happen within boundaries. So one day it may be on time or in a frame space. Intervals of time, right? The boundary may be interval of times. Measuring occurrences within a specific minute, 1 hour, 1 day, how many likes you receive in Instagram, how many shares or how many comments you get in a TikTok, how many shares in minute, hour, or day. Interval of space, so interval of time, interval of space. As I told you, the book example. Measuring occurrences within a specific page or square meter or district. Here the district, there are many people. How many of them got accident? Or how many houses are got fire? Square meter. When you purchase cloth material, fabric, then there are chance of getting damaged. A discrete, so the probability distribution is a discrete probability distribution used when our interest lies only on the number of occurrences of a certain event, not not its non-occurrences. So in the binomial distribution, we are considering only the success. We focus on occurrence that we refer success. Here we consider only on the occurrences. Occurrences mean here ATM. We are considering how many customers visit to the ATM. We are not considering how many customers are not visiting. How many messages you are receiving. We can't say how many messages we are not receiving. Those are impossible. No? So in Poisson distribution, we are not considering non-occurrences. We are not consider non-occurrences. Let's see some examples. Recognizing Poisson process in the business world. Here, customer queue in a bank. Arrival of customers at a service station. It may be the bank or railway ticketing service station, bus booking setup, or petrol set queue. Switchboard. In a large corporations, they have intercom. They are having hotline. It receives calls, right? So from after that, they will divide that call for particular units using intercom. Here switchboard. So that particular switchboard, how many times, how many calls it receives, telephone calls arrived at the switchboard. Automobile, accidents occurring at a certain junction each day. Magnifying glass or floor, defect in each 100 square meters area on a tiled floor or in fabric. If you need a staff shift, or you need to find a fund of a risk pool, so the insurance companies, many of them are insured against any loss, business loss. Loss mean the fire or accident or flood. So during that instances, they want to know how many claims they may get, claim application they may get. So that accordingly they have to make arrangements of fund. And quality control, and you need Poisson distribution for these instances. The three golden rules of Poisson process. If you want to apply a Poisson distribution for a business scenario, you should know, you should have three conditions. This means to apply Poisson process, it should satisfy three criteria. First one, a constant probability. Constant probability over the time, over a certain interval of time or space, the probability of the event occurring is constant. For example, if you found you receive WhatsApp messages every day 20, this means normally you may get 20 messages probably, right? That's and defective items. A machine produces 100 items, 20 items may be defective. So this is constant, almost it's constant. Someday 20%, someday 50%, someday 1% defective. No. So that kind of things we are not considered. We can't apply for Poisson process. And strict independence. One event may not affect another event in the same space, time or space. The occurrence of one event is not dependent on another occurrence of that event. So independent. No simultaneous event. In a very small interval of time or space, the probability of two or more events occurring at the exact same time is negligible. For example, switchboard, telephone, switchboard, it receives calls. Here we assume that when the officer deal with one call, sometime there's a chance of getting another call at the same time. So in our term we call it a waiting call. So that instance is that instances we consider negligible. It's rarely happened. It's an assumption. It's very, in a very small interval of time or space, the probability of two or more events occurring at the exact same time is negligible. For examples, if a test question violates any of these three rules, you cannot use Poisson formula. Keep remember. And now we move to the formula for calculating Poisson probability distribution under Poisson. So Poisson probability distribution. Here is a formula, probability x. Here px mean the probability of exactly x event is happening. So for example, exactly 5 calls, receiving 5 calls, or probability of getting happening 5 accidents, like that. Here this part, this is E, right? What is E? E means here E has it has some value, a mathematical constant. Just hit the button, E button on your calculator, it shows you 2.718. Let's see, I can show you for demonstration. Here, this is your calculator. Then you can find E. So where is E? Here, shift E. Right? Then the value is what? E. 2.71828. Here, we get the same figure. 2.718. Here E is this value never change. This value never change. It's always 2.718. 718, and here lambda, you can see a lambda, it's a negative lambda. Lambda means it's a mean, right? It's a mean. Lambda, the average, the mean. How we calculate lambda? Very simple, straightforward. NP, number of trials and probability of success. Probability and number of trials. This is the only parameter you need to know. Right here, it's very straightforward. You see, it's a very straightforward thing. E, that's 2.178. Here lambda minus lambda into lambda. So actually, very careful. This is power, right? This lambda is power. This is normal value and it has power that's equal to this x. And it should be divided by x factorial. X, the target number of occurrence you are testing. Say, for example, the probability of getting 5 customers in a time. So then x equal 5. This is the formula. Now we move some questions. An ultimate time server, right? Mean equal variance. In the Poisson distribution, mean, right? Mean equal variance. So here mu, so lambda equal, lambda means mean, no? Mean, or average. This is average. And here, how we calculate? So lambda means mu, it's mean, or that's equal what? Variance. Mu equal lambda and variance. Lambda. So standard deviation, simply square root of lambda or square root of variance. Very simple. Square root of lambda or variance. Because Poisson has a single parameter, lambda, if a question gives you the variance, you automatically know that variance equal mean. Here one case study example, the call center. Here is the example. A telephone switchboard in a firm receives on average 90 calls. It receives 90 calls per hour. Find the probability that during 1 minute interval, the switchboard will receive 0 calls. So normally, in the company, it has a telephone switch. It receives 90 calls per hour. Now, the question is asking, getting 0 calls in 1 minute. The details given in hourly basis, but the question on minutes basis. Now we convert. Here 90 calls for 60 minutes. Then how many calls per minute? 1.5. Therefore, on average, the switchboard gets 1.5 calls per minute. It receives 1.5. It's an average. Now, the question, the probability of getting no calls, 0. Here, probability 0. So very simple, right? E minus lambda and lambda and lambda and x factorial. At, yeah, sorry, and x. Here in this case, Here lambda, we know E equal to 2.718, lambda minus 1.5 into 1.5, and x equals 0 and x equals 0 factorial. So when we solve this, we can find the probability of getting 0 calls. So we can apply this one. I can use the calculator here. So I think we don't want this. Right. Here I apply this one and 2 point. Sorry, we don't want this 2 point. Here directly we can apply E and 2 and 1 point minus 1.5 into 1.5 power 0 and 0 factorial. Then we can get the answer 22.31. 22.3. See the answer here. Executed the baseline formula here. Some of the diagram. So in 1 hour, it gets 90 calls, and we need only for 1 minute. The scenario: a firm telephone switchboard receives on average 90 calls per hour. The objective is find the probability of receiving specific call volumes during 1 minute. So therefore we have to find the lambda. Lambda means average 1.5 calls per minute. Always adjust lambda to match the time interval asked in the question before touching the main formula. So we did. Always remember. Here we apply the formula here. Probability of getting 0 calls, E 1.5 minus 1.5 into 1.5 the x0 and 0 factorial. So its value to 0.2232, as we get the same answer, 2232. And the probability of getting one call, so we little change the formula. We change the formula in little. Here we change this one. Here x value, here 1, and here 1 factorial. Here we have to apply 1 factorial, and here 1. Here in the calculator, here I don't want to edit everything, just I edit 1 call, and here put 1. It's equal 3347. So it's 3347. Let's check the answer. Here we get almost similar answer. Here 3348. Here also 3347 is answer. Why we get the different answer? They apply this value, but it's approximate value, but we use exactly E. And the third question, getting exactly 2 calls. So we just replace this 2 factorial. Here just we change this one, and here 3, right? The getting exactly 3 calls. We just change is 3 and 3 factorial. And here it's simple. We make it in 3. It's equal 0.1255. Okay, 1255. And more than 3 calls. So more than 3 calls. In 1 minute interval, on average it receives 1.5 calls. Now we have find out a probability of getting 0 calls in a 1 minute, in a minute, and exactly 1 call, exactly 2 call, exactly 3 call. Here on average 1.5, 1.5. So look at the probabilities here. Notice here the probabilities. Receiving 0 call probability is 0.2, only 22%. Receiving 1 call, 33%. Receiving 2 calls, 0.25%. And receiving 3 calls in a minute, 12%, only 12%. Have you observed? So the average, the value, right? The value, the number of calls, it's similar to or approaches the average 1.5, 1.5. The call here approaches the mean. You can observe that it has large probability, but it deviates from the mean 0 here, and the probability is 22%. And 3 calls here, 3 calls, 12 almost 12%. So notice how the probability peak at one call, since our average is 1.5. It's mean between here. So we can't say what's the probability of getting 1.5 calls. So that's fundamentally wrong. Why? It's a discrete probability distribution. And being dropped as x increases, the number of call increases, the probability also drops. And one more point I want to emphasize you here, more than 3 calls. So we can get in a minute, we can get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You go to infinite number of calls in 1 minute. There are possibilities. So what's the possibility? To calculate that, what you have to find, what you have to do, you have to find a probability of 3, probability of 4, probability of getting 5, 6, 7, 8. So we have to calculate probability for each. That is difficult. But what we can do is, we can find the probability of getting no call, getting 1 call, getting 2 call, and getting 3 calls. Then we sum all these 4 probabilities, and we deduct from 1. So that 1 minus probability of interest, then we can get the complement. We can apply complement rule. Here, the question, what is the probability of receiving more than 3 calls? More than 3 calls, not equal to 3. The trap, trying to calculate P4, P5, P6 all the way to infinity. To save your time, the complement rule, right? Complement. We have discussed this one when we discussed the fundamental of probabilities, from the probability laws. The solution, what we can do is the probability of getting x more than 3, getting calls more than 3 is equal 1 minus probability of getting call 0, 1, 2, 3. So that we can get this value. So that we already found probability of getting 0 calls is here, probability of getting 1 call, probability of getting 2 calls, probability of getting 3 calls. Then we get 1 minus sum of this here, 0.06. 0.06. So 93% chance, 93% chance getting calls 0 to 3, 93%. More than that, very rare case. So four calls, rare. 5 calls, very rare. 6 calls, very rare. 15 calls, it's right, almost zero chance, almost impossible. And now we look at case number 2, example number 2. It's regarding modeling population risk. In a certain district, on average, one house for every 500 houses has fire during a year. There are 1,000 houses in this district. Calculate the probability. So what is the probability of getting fire? 1 over 500. Yeah, one house for every 5 houses has fire. It's not a time, it's a space. It's a space. 1 year space, 1 year time, 1 year space. So there are 1,000 houses in the district. Calculate the probability that exactly 5 houses will have the fire during the year. Here, the trick is to apply the Poisson distribution. We should know the lambda, the average. Here, on average, there are 1,000 houses, and we know the probability is 1 over 500. It is based on NP principle. We discussed this one, expectation in the previous class. I have shared the recording as well. NP expectation equal NP. N is number of repeated trials, and P is a probability. So expectation is here 2, right? Lambda equal 2. On average, among 1,000 house, there are chances of getting 2 houses got fire. There are chances. On average, 2 houses will got fire out of 1,000 houses. Now we apply this. We apply the probability Poisson distribution exactly 5 house. So it's very simple. E minus lambda, that is 2 and 2, and x with 5 and 5 factorial. Straightforward. Yeah. Yeah, I want to change only I can start again. Yeah, I use this one, and E minus 2 2 power 5 and 5 factorial. So the chance is 0.036. So 0.036. Let's check the answer. Yes, we get the exactly same answer. Exactly 5 houses. More than one house. What's the probability? We can apply complement rule. Rule here 1. All the sum of probability equal 1. We can calculate probability of 0, probability of 1, getting 5. So we can apply here we can apply 1 minus E, that is minus 2 into 2 power 0, and 0 factorial is always 1. 0 factorial is always 1, we know that. And plus E power minus 2 2 power 1 factorial is 1. 1 factorial is 1. So, and we close the bracket. 59 point. Here you can see the answer. 0.5939. 0.1939. So this is how we can apply the complement rule of the probability. And another section we are considering, sometime we can apply Poisson distribution for binomial distribution. So it's called approximating the binomial distribution to Poisson distribution. We know that the formula for binomial distribution is NCR, PX or PR, NCR, right? So the usual formula we apply NCR, P, Q, R, N minus R. So this is the binomial distribution. But we can apply sometimes. There's a two rules, two conditions. If these two conditions are satisfied, we can apply Poisson distribution. We can apply Poisson distribution for binomial distribution, and we will get similar answer, almost similar answer. Here, what are the conditions? Binomial distributions require knowing the number of trials. That means n. Here we need, right? We need n, and probability of success p. Calculating this for massive population is mathematically exhausting, right? It's if it is very large amount, and it may be difficult. Calculation may be difficult. When n becomes very large, say more than 50, and p becomes very small, like 0.2, 0.01, like that, probability is very small, the binomial distribution elegantly approaches the Poisson distribution. So binomial distribution act like a Poisson distribution. So we can use Poisson as shortcut by setting, right, by just finding lambda. Lambda means no expectation, NP, number of trials, probability of success. Here the rules of engagement for approximation. You can only use the Poisson approximation if two conditions are met. Two conditions are met. Condition number one, the sample size is large. Here, right? Sample size should be large. You can apply. You can use Poisson distribution instead of binomial distribution if the number of sample size is more than 50, and also the lambda should be less than 5. Lambda means what? The probability of success is tiny, very small. NP is less than 5. Lambda should be small, less than 5. Always physically write out the n more than 50 and NP expectation, the average is less than 5. Check on your exam paper before applying approximation to secure full mathematical marks. It's an example tips. Here, let's see one example. It is found that 2% of the items produced by a machines are defective or non-defective items, right? Success, defective, getting defective item is success, P. So therefore, P is very small, that is 0.02. 2% mean what? 0.02. A random sample of 100 items produced by this machine is investigated. N equal 100. The repetition is more than 50. Find by using binomial distribution the probability of getting exactly two defective items. We know the formula. So this is actually binomial distribution. Why? So it has two outcomes: defective, non-defective items. We know the probability of defective item average is 2%, right? 2. Now let us apply this Poisson binomial distribution NCR n equal 100, C combination, R equal 2, exactly 2 defective item, P is 0.02 and R equal to Q equal 0.98, Q equal 0.98, and this is what? 98. So when we apply this, let us check the probability. See, 100 2 into 0.02 power 2 into 0.98 power 98. We get 23.34. 23.34. Now let us apply the Poisson distribution for the same scenario, so that we need to find the lambda. Lambda is a mean NP. So n here 100, P equals 0.02. So therefore it's 2. It is 2, NP equal 2. Now let us apply a Poisson distribution. Here E lambda minus 2, 2 and x equal to and 2 factorial. Yeah, E minus 2 minus 2 into 2 power 2 factorial is 2. You see, we get the exactly almost similar answer, right? Let us check the answer. We had some mistakes there, right? Here we get the similar answer. Right. So notice how closely the values match the Poisson shortcut. The Poisson shortcut save the time and minimize calculator error. Yeah. Setup here 2% deduction defect rate. So P equals 0.02. Sample size is 100. And find the probability of exactly 2 defective item x equal to the condition check. Number n equal 100, it is more than 50. NP is less than 5 is 2. Approximation is approved since lambda is equal to. And we have called NCR. We apply NCR, binomial distribution. It looks hard, and a smart way, that's applying the Poisson distribution, getting probability of defective items. Yeah, we almost get the similar answer. Right, then you can find check for the suitability of the Poisson approximation, and by using Poisson approximation find the probability of getting 2 defective items. Right, 2 defective items we already found using both models. Now let us check the less than 2 defective item. Less than 2 defective items, simply probability of 0 plus probability of 1. Less than 2, not 2, right? So 1 minus, not less than, so not 1 minus. Here, if we add these two, we can answer for this question. Here, 1 did for you. Probability of getting less than 2 defective items. Here, probability 0, probability 1. Here, we applied which one? Poisson distribution. Here instead of, originally this is a binomial distribution function, but here we apply Poisson distribution. Here in this answer is given in the Poisson distribution. Now let us try to use binomial distribution to check the answer, to make sure the answer is correct. Right. Now, yes, we want to make it 0. This is Poisson, no? Yes. Now so the question is applied on Poisson. We apply binomial distribution. NCR n 100 C and C 0. NCR R equals 0 into 0.02 power 0 into 0.98 power 100, no? Yes. Equal what? It is 0.1326. 1326. This is P0. Right. Again, we move forward. Right. C R equal 1 into 0.02 power 1 into 0.98 99, 99, and we close the bracket. Altogether, right? Here we got the same answer, right? Here, Poisson distribution give us 0.4061, and binomial distribution give us almost same answer, 4032, right? And now probability of getting at least two defective item. At least two defective item. Here we have to consider at least two. Mean what? 2, 3, 4, 5, 6, 7, 8 to infinity. So we already know the probability of getting less than 2. So 1 minus less than 2, we can get more than 2 defective items. Probability of getting at least 2 defective items, the probability sample here 2, 3 to 100. So 1 minus here we can get 0. 0.5939. So it's straightforward and simple. Let's see the summary of today's session. Your business statistics cheat sheet. So core math formula is this for probability distribution, Poisson distribution is this, and the mean, don't forget, in Poisson distribution, mean equal variance. Sometime in your exam questions, they may give you variance, then you should know. Or sometimes they may give you standard deviation. So you should know the square of standard deviation is equal to variance. Variance equal to mean in context of the Poisson distribution. And E, the value is 2.718. And the rules constant to apply the Poisson distribution. There should be a constant probability, and the events should be independent. No simultaneous occurrences which are negligible. If so, a binomial approximation allowed only when n more than 50 and the expected lambda less than 5, right? So lifesaver, so it's an approximation binomial to Poisson distribution. So more than x questions, don't calculate to infinity, so use complement. Example, probability of more than 1 equal 1 minus probability less than 1. That is mean probability equal to 0 plus probability equal to 1. That's all about today's session. If you have any questions, you can unmute your mic and you can ask.